all. This is lecture 13 on 4.4 called implicit differentiation. So there's multiple things that are a consequence of the chain rule, and one of those things is implicit differentiation. So first, let's talk about the difference between an implicit function and an explicit function. So you're used to explicit functions where we write either y equals or f of x equals, and then we specify some function of x. But that's not necessarily the only way to define a function. So you can define a function such that you have x's and y's that are all mixed together, right? X squares, y's. And in this case, if you tried to solve this for y, you wouldn't be able to do it, right? And that has to do with the fact that I've got a y squared term here and a y term here. So if I tried to collect them and divide it, it wouldn't work. Okay, but that doesn't mean that y isn't still a function of x. In this case, y is still a function of x. And so what we want to be sure is that when we go to differentiate something like this, we need to know how to handle the fact that you're differentiating a function of x. Okay, that y has a hidden function of x in there. So the key to implicit differentiation is that whenever you differentiate a y, you must multiply by dy dx. And here's why. So let's suppose we had a function like y squared, right? And y is really, let me rewrite that. Let's say y is really some function of x that we don't know, some g of x. So really, this is g of x squared, right? So if you look at it that way, we would use chain rule. So if you were taking the derivative of this term, then you would have to take the derivative of the outside function, which is the square. So you would bring down the 2, and you would leave the y on the inside. But then you'd have to differentiate the function that's inside, right? So we don't know what that is. We just know that it's the derivative of y with respect to x. So we would multiply by dy dx. And so for every time that we get a term, that we differentiate a term with a y, we have to multiply by dy dx. Okay, so it's going to look something like this. Take a look at example 1. We've got y squared plus x squared plus 5y plus x equals x cubed minus 4. And we want to go ahead and take the derivative of this implicit function. So what we're going to do is we're going to term by term take the derivative. And anytime we take the derivative of a y, we're going to remember that we need to multiply by dy dx. Okay, and then we're going to solve for that dy dx. So here we go. First thing, derivative of y squared. The derivative of y squared is 2y, but it is a y, so I'm going to have to multiply by dy dx. Derivative of x squared is 2x. The derivative of 5y is 5, but you have to multiply by the derivative of y, which is dy dx. Okay, dy dx is just another notation for derivative, where you're taking the top references the derivative of the function, and the bottom refers to the variable that you're differentiating with respect to. So we're differentiating the function y with respect to x. Our next term is the plus x, so that's going to give us plus 1. And on the right, the derivative of x cubed minus 4 is 3x squared. Okay, now what I want to do is I'm still trying to state explicitly what the derivative is. So this represents the derivative and this represents the derivative. So I want to solve for dy dx and write it as dy dx equals, okay, so that I have the derivative explicitly in terms of x's and y's. So what I want to do is I want to keep any term that has a dy dx on the left-hand side where it is now, and I'm going to move anything that doesn't to the other side. So this 2x I'm going to subtract to the other side, and this 1 I'm going to subtract to the other side. And when I do that, I'm going to be left with 2y dy dx plus 5 dy dx equals 3x squared minus 2x minus 1. Okay. Now, I've got only the terms with dy dx on the left. So here's 1 and here's 1. And so I'm going to factor that out because they both have a dy dx in common. So we're going to take the dy dx out front. We're left with 2y plus 5. And then I want to solve for dy dx, so I'm going to divide both sides by 2y plus 5, and that'll get me the dy dx by itself. And so now I have that the derivative of y with respect to x is 3x squared minus 2x minus 1 all over 2y plus 5. And that's my derivative. Now notice that my derivative is in terms of both x's and y's. And so if you're going to find a value, suppose you want the equation of the tangent line, you're going to have to plug in your x value and your y value in order to find that slope of the tangent line, all right, which is represented by the derivative. Okay. Another thing to note here is that note that anytime you see a y and you differentiate it, it pops out a dy dx. And those terms ended up on the bottom of my fraction. So if you think about it, any term that had an x in it ended up in the numerator, right? Because there was no dy dx when you differentiate an x. So it ended up on the right-hand side of my equation before I divided. And that ended up in the numerator right here. So if I go back and look at my original equation, I should see 3 terms that have x's in it and 2 terms that have y's in it because I have 2 terms on the bottom. And you can see that I do. If you look at this, let's see, I've got 2 y terms. And I've got 1, 2, 3 x terms. And that tells me that I have 3 in the numerator and 2 in the denominator. And that's consistent with what I have in my answer. So that's kind of a quick check that you can make to be sure that you've made sure you didn't lose any dy dx's. Let's look at a couple more examples. Oh, whoa, this one got a little bit crazy. I think this is supposed to be 2 problems. So let's do this. First of all, let's get rid of this one for now. Actually, this one's the same one we just did, right? So let's get rid of that and we'll do this one over here. Okay, so let's tackle this one. So we have y squared plus x squared equals 2xy plus x squared plus 1. Okay, now, so here's some things. You can actually simplify this and rearrange this ahead of time if you wanted to. So notice that there is a plus x squared and a plus x squared on each side. So if I subtracted x squared from each side, I'd simplify this and it would cancel out, okay, because you're working with an equation. But I'm going to leave it as is, and we'll see that that's going to cancel later on. Now, the other thing I want you to notice here is right here. Right here, I'm multiplying 2 times x times y, and that's going to require me to use a product rule because I'm multiplying functions together. So keep in mind that all of your derivative rules still apply. So when I differentiate y squared, that's going to give me 2y times dy dx. So I'm moving left to right. Plus derivative of x squared is 2x equals... Now, for 2xy, I'm going to go over here and write things down. So I'm going to take the 2 with the x. You have multiple options with the 2 when you're working product rule. You could leave the 2 out front and just do the product rule with the x and the y. I like to just put my 2x into function 1. And that way it has a place and I can take the derivative of it and it's not a problem. So 2x and 2. And then I have, function 2 is just y, and 2 prime is going to be 1, except it's a y, so it's dy dx. And that way, when I put that back together, we have 1 prime 2, so that's 2y, plus 2 prime 1, so that's 2 times x times dy dx. And then the derivative of x squared plus 1 is going to be just plus 2x. Now, what I want to do is I want to move everything with a dy dx to the left and everything without a dy dx to the right. So the first thing I'm going to do is go ahead and subtract that 2x. And now you can see that they do, in fact, cancel each other out. And that leaves me with 2y dy over dx equals 2y plus 2x dy dx. And now I've got to move that dy dx to the other side. So I've got to subtract 2x. And I'll do it in a different color, minus 2x dy dx from both sides. Okay, so what I'm left with here is negative 2x dy dx plus 2y dy dx equals 2y. Okay, now you can also notice that every single term has a 2 in it. So you could cancel a 2 in each term. Then what I'm going to do is I'm going to factor out the dy dx. I'm running out of room here. So if I factor out the dy over dx, I'm left with negative x from the first term on the left plus y, and that's equal to y, right? I canceled the 2's. And the last thing we want to do is to divide through. So divide both sides by negative x plus y, so that gives me y over negative x plus y. And that's my final derivative. Again, if I check, now be aware that I could cancel those x squared terms. So if I cancel the x squared terms, then I have one term with an x and two terms with a y. And that's exactly what I have here. One term in the numerator, two terms in the denominator. Okay, so here's example 3. Here's another one where we've got some product rule happening. So here I'm multiplying x times y, so I'm going to need a product rule for that. So function 1 is going to be the x, and its derivative is 1. Function 2 is going to be the y, and its derivative is dy dx. So using product rule, 1 prime 2 is just y, plus 2 prime 1 is x times dy dx. That takes care of the first term. Now we have minus y cubed, so that's negative 3y squared dy dx. And the derivative of 4 is 0. From here, we're going to move that y to the other side. And I'm going to right away factor out the dy dx just to keep things moving. So when I take the dy dx out, I have x minus 3y squared. And on the right, I have negative y. And then we divide, so dy over dx is negative y over x minus 3y squared. Okay, so those are 2 examples where you've got product rule happening. You can also have chain rule. I'll be right there. You can also have chain rule. So notice in this one, I have an inside function and I have an outside function. So when I go to differentiate this, I'm going to start with my outside function. So the derivative here would be 10. We bring down our power, leave the inside alone, decrease our exponent by 1. Then we take the derivative of the inside, and the derivative of the inside is 1 plus, and then the derivative of y squared is 2y, but it's a y, so I need to multiply by dy dx. And that's my derivative on the left-hand side. On the right-hand side, my derivative is just 2x. Okay. Now, I only have one dy dx. I just have to solve for it by uncovering things. So I'm going to work my way out from the outside to the inside. So the first thing I'm going to do is divide the both sides by 10 times x plus y squared to the 9th. If I do that, I'm left with 1 plus 2y dy dx on the left. And I have 2x over 10 x plus y squared to the 9th. Then I'm going to go ahead and subtract a 1 because I have a 1 over here. So subtract 1. So that gives me 2y dy over dx is 2x over 10 x plus y squared to the 9th minus 1. And then I'm going to multiply both sides, or divide both sides by 2y, but because I've got fractions, instead of dividing by 2y, I'm going to multiply by 1 over 2y. And that's going to make it a little bit easier for me to do the algebra. So that leaves me with just my dy over dx on the left, which is what I'm looking for. And then when you distribute your 1 over 2y, the 2's will cancel, and I have x over 10y times x plus y squared to the 9th minus 1 over 2y. Right? If you want to get common denominators, you can, but I'm happy to leave it just like that.